Welcome to the Deep Dive, where we take complex research and, well, unpack it into surprising facts and essential insights for you. Today, we're embarking on this really incredible journey, not through space, but way back in time, almost 500,000,000 years, actually. We're going to try and uncover Earth's ancient temperature story.
That's right.
Have you ever wondered how scientists figure out what the temperature was like, millions and millions of years ago? Long before thermometers or satellites?
Yeah.
Heck, before dinosaurs even existed.
Yeah, it's definitely not as simple as checking a fossil's forehead.
Definitely not.
But indeed. Our deep dive today is into a truly groundbreaking study by Emily J. Judd and her team. It's titled A 485 Million Year History of Earth's Surface Temperature. And they've basically built the most detailed temperature record ever for the last 485 million years.
Wow.
This huge chunk of time geologists call the Phanerozoic Eon. It covers, pretty much everything from the first complex life right up to today.
Okay, so our mission today is to explore the ingenious detective work they used, how they pieced together this ancient climate puzzle, understand the incredible challenges they must have faced,
Oh, absolutely. Huge challenges.
and ultimately reveal what their findings tell us about our planet's long, dynamic thermal history.
Exactly.
Get ready for some truly eye-opening insights, folks, into how Earth has actually behaved across geological time. Okay, so let's unpack this. It sounds like a monumental task.
Yeah.
How do you go back 485 million years to read a thermometer that simply doesn't exist? This study uses a technique called data assimilation. What does that actually mean for, trying to understand Earth's past?
Right. Think of it like this, maybe. Imagine trying to reconstruct a really old, faded map. You start with a general sketch. That's your climate model. It gives you a broad idea of where things might have been, the general climate patterns.
Okay, like a basic outline.
Exactly. But then you find these tiny, fragmented pieces of the original map. These are your proxy data. They're like little chemical clues preserved in ancient rocks and fossils. Data assimilation is the process of precisely fitting those real fragmented clues onto your general sketch. You use them to refine it, correct it, and create a much more accurate, detailed map of the past climate. It's about combining the best predictions from these powerful computer models with direct, albeit, indirect evidence from Earth's own history.
That's a great analogy.
Yeah.
So what kind of clues are we talking about here? We're definitely not finding ancient weather reports tucked away in rocks.
No, not quite.
So what did these scientific detectives actually use?
Well, the team compiled this huge data set, over 150,000 of these proxy clues. But they're not scrolls. They're tiny chemical signatures preserved in things like ancient marine shells and rocks. You can think of them as miniature natural thermometers.
It's actual thermometers.
Yeah. They looked at things like different types of oxygen isotopes. These are specific forms of oxygen atoms. Their ratio changes based on the water temperature when the organism was alive. They also analyzed ratios of elements like magnesium to calcium in ancient shells, and even some unique organic molecules preserved in ancient sediments.
Wow.
Each of these chemical fingerprints told them something specific about the temperature of the ancient seawater where and when that sample formed.
That's fascinating. But with data that old, 485 million years, you must have to be incredibly careful. How did they make sure these tiny clues were actually reliable?
That's a really critical point. And yeah, the team went to absolutely painstaking lengths. They had to filter out any data points that look like they might have been altered over time by geological processes, or data that came from, say, unusual environments like hypersaline lagoons, which wouldn't represent the broader ocean conditions.
Right, you want the typical ocean, not some weird salty pond.
Exactly. It was like sifting through millions of slightly blurry, sometimes smudged old photographs to find the clearest ones, the most reliable signals. And even after all that meticulous screening, they still had nearly 120,000 highly reliable proxy values to work with. That sheer volume and the quality control is really what makes their reconstructions so robust.
Okay, and on the model side, what did that involve? Because these aren't just simple weather apps running on a laptop, right?
Oh, far from it. They used a really powerful climate model called HAD-CM3L. It's one of the leading tools for simulating Earth's long-term climate. So to get that initial general sketch of Earth's past climate, they ran simulations for 109 different time slices across this whole Phanerozoic period.
So taking a snapshot every 5 million years or so?
Pretty much, yeah. Approximately every 5 million years. And what's truly impressive here is that For each of those time slices, they ran the model multiple ways. They explored different levels of atmospheric carbon dioxide CO2 from levels similar to pre-industrial times up to 4 times that amount.
Okay, testing different scenarios.
Right. And this resulted in just an astonishing amount of computation. We're talking over 2.5 million years of simulated climate data.
Whoa.
That gave them this incredibly rich, detailed starting point, or prior state, as they call it, for their assimilation process.
Here's where it gets really interesting for me because dealing with ancient data, I mean, it inherently means dealing with a lot of uncertainty, right?
Absolutely.
And this study seems to have gone to great lengths to address that, not just errors in lab measurements, but the very nature of the clues themselves.
You've hit on a key aspect. A really critical part of their method involved defining what they called proxy covariance. It's basically a sophisticated way to quantify the inherent uncertainty in each and every data point.
Okay.
And it's not just about, how accurately you can measure something in the lab today. It also accounts for things like vital effects. That's how different organisms might naturally incorporate elements slightly differently, even in the same water.
Biology messing things up.
Well, adding complexity. And it also accounts for changes that might happen after the organism dies, diagenesis, as the shell or rock sits there for millions of years. They even ran specific experiments to try and pin down low, medium, and high levels of uncertainty for each type of chemical clue.
That's thorough.
Very. For example, they noticed that some of the older magnesium to calcium data, the micrea, consistently seemed to suggest warmer temperatures than other types of proxies from the same period. So they carefully increased its assigned uncertainty value. This ensures it didn't unfairly skew the overall picture just because it behaved a bit differently.
So they're essentially weighting the evidence based on how reliable they think it is.
Exactly. It's about acknowledging the known limitations of your evidence and building those limitations right into your final result. It makes the end product much more honest and trustworthy.
Okay, so it's not just about temperature itself. The chemistry of the ancient ocean plays a huge role in how these natural thermometers actually work. I understand they had to make some crucial assumptions or maybe estimations about things like the oxygen isotopes in the seawater itself and its pH, its acidity. Can you tell us more about those foundational chemical puzzle pieces?
Yes, absolutely. Those oxygen isotope thermometers we talked about, their readings are also influenced by the isotopic composition of the seawater the organism lived in. Over these vast timescales, the biggest factor changing that is global ice volume.
Ice sheets. Okay. How does that work?
Well, when massive ice sheets grow, like during an ice age, they preferentially lock away the lighter oxygen isotope, oxygen-16, into the ice. This leaves the remaining ocean water relatively richer in the heavier oxygen-18. So the isotope ratio in a shell changes not just with temperature, but also with how much ice is on the planet.
Okay. So you need to correct for that.
You do. To get accurate temperature readings, they had to estimate how much ice was likely on Earth during each time slice and adjust their calculations accordingly. They used modern records of how isotopes change with ice volume as a kind of template.
But I seem to recall there's been some debate about this in the past, right? Did the baseline oxygen isotope composition of seawater itself, fundamentally change over millions of years, independent of ice? That seems like it would really throw a wrench in the works.
That raises a really important question, and it's actually a point where this study really shines because of its rigor. Yes, there are theories suggesting a long-term fundamental shift in the baseline composition of seawater, maybe due to changes in geological processes like hydrothermal activity over millions of years. The Judd team specifically tested one prominent hypothesis put forward by Weiser and Prokop, often called VP15. It suggested a pretty large, gradual increase in the heavier oxygen-18 in seawater since the Ordovician period, way back.
Okay, so they tested that idea.
They did. They applied this VP15 correction to their proxy data. But when they did that, the reconstructed global mean surface temperatures they got became, well, frankly, unrealistically cold for the early Paleozoic era.
How cold are we talking?
So cold they were getting sub-zero global average temperatures in some periods, which just doesn't line up with any other geological evidence we have for life thriving at that time.
Right, that doesn't sound right.
Exactly. And what's truly fascinating here is how they validated this. They didn't just say, this looks weird. They compared their VP15 corrected results with completely independent temperature estimates from something called clumped isotope data. Clumped isotopes measure temperature using a different chemical principle altogether. And the VP15 corrected temperatures were wildly inconsistent with these independent records, sometimes more than 15 degrees Celsius colder during certain ancient periods.
Wow, 15 degrees difference. That's huge.
It's enormous. This external validation clearly showed that the VP15 assumption, at least as proposed, was unrealistic for their dataset, so they could confidently exclude it from their final main findings.
That's a great example of how science works, testing hypotheses against different lines of
It
evidence.
really is. It shows the process of self-correction and refining understanding based on robust testing.
So that covers the temporal variability, how ocean chemistry changed over time, especially with ice ages. But what about spatial variations? Did it matter where in the ancient ocean a sample came from, like differences in salinity?
Absolutely. Just like today, ancient oceans weren't perfectly uniform. They had variations in salinity, saltiness, mainly due to evaporation and precipitation patterns. And these salinity differences also correlate with oxygen isotope values locally.
Another complication.
Another complication they tackled head-on. To account for this, they developed a really sophisticated statistical model. They call it a spatially varying analog regression model.
Okay, bit of a mouthful. What does it do?
In simpler terms, this model used various climate parameters predicted by their HAD-CM3L climate simulations. Things like the local sea surface salinity, the local temperature compared to the global average, even how close a point was to an ancient coastline. It used all that information to predict what the local oxygen isotope value of the seawater should have been at any given location back in deep time.
So it customizes the correction factor for each sample location.
Essentially, yes. And they rigorously tested this spatial model against modern ocean observations and also against other climate simulations for ancient periods, and found it performed very well. It allowed them to account for those important regional variations in ocean chemistry, not just rely on a single global average correction.
Okay, one more chemical factor.
Yeah.
What about ocean acidity? That's obviously a big topic today with climate change. Did it also, throw a wrench in the works for these ancient temperature readings?
It definitely can. Seawater pH or acidity also affects the way shells incorporate elements like oxygen isotopes and that magnesium to calcium ratio we mentioned. And since we know atmospheric CO2 levels varied hugely over the Phanerozoic, sometimes much higher than today, ocean pH must have varied significantly too. More CO2 generally means more acidic oceans. So the team was very thorough here. They actually used two different approaches to estimate past pH levels for each time slice, both derived from their climate models and their own CO2 reconstructions. By including both approaches in their assimilation scenarios, running literally hundreds of different permutations for each geological period, they could ensure their final temperature results properly accounted for this pH uncertainty.
So they bracketed the possibilities.
Exactly. And they specifically noted that if they hadn't included this pH correction, their reconstructed temperatures would have appeared spuriously colder during past greenhouse periods. They would have underestimated how truly warm those ancient warm periods actually were.
Okay. So after all this incredible, meticulous work combining the powerful models, thousands of these tiny chemical clues accounting for ice volume, spatial chemistry, pH, uncertainty, what does Fanda ask? That's the reconstruction, right?
Fande, yes. Phanerozoic data assimilation.
What does Fanda actually tell us about Earth's 485 million year temperature history? What's the big picture emerging from all this?
Well, the big picture presented by Fande is a climate history that is both more variable and, importantly, warmer overall than many previous long-term reconstructions had suggested. This is especially true during Earth's past greenhouse intervals, those periods thought to be naturally very warm. Fande shows a greater swing, a bigger difference between Earth's hottest and coolest periods over this vast timescale.
More variable and warmer overall.
Yes, it reveals a planet that underwent even more dramatic climate shifts than perhaps we previously understood based on older, simpler methods.
And why is this reconstruction coming out warmer and more variable than some of the earlier studies we might have seen? What makes Fanda different?
Yeah, there are several key reasons for that. Firstly, because Fanda uses data assimilation, its results aren't fundamentally limited by the base climate sensitivity programmed into the climate model itself.
Meaning the data can override the model's basic tendencies.
In a sense, yes. The actual proxy data exert a strong influence, pulling the reconstruction towards what the real-world evidence indicates, even if that pushes the temperatures beyond what a standalone model might have predicted based on CO2 alone. Secondly, that pH correction we just discussed is really crucial. Many earlier studies didn't fully account for how changing ocean acidity affected the proxy readings during past greenhouse periods.
And that made them look cooler than they were.
Exactly. It likely led them to underestimate just how warm it truly got back then.
Okay.
And finally, this study incorporated a vastly more extensive and, as we discussed, rigorously vetted compilation of proxy data. They particularly focused on planktonic, foraminifera, tiny marine organisms, but also included additional proxy systems beyond just the traditional oxygen isotopes.
So more data, better quality control, better chemistry corrections.
Pretty much. It's simply a more complete and carefully analyzed data set combined with a more sophisticated method, leading to what they argue is a clearer and, yes, generally warmer picture of the past.
This level of detail must reveal some really interesting things about how Earth actually transitioned between different climate states. From icy periods, ice houses, to really warm ones, hot houses. Are there any particular periods that stand out in the Fandier record?
Oh, absolutely. The study formally defines 5 climate states based on the reconstructed global mean surface temperature. They call them cold house, cool house, transitional, warm house, and hot house. But what's truly fascinating, and maybe counterintuitive, is that the global average temperature isn't the only story, especially when it comes to figuring out how much ice was around.
How so?
Okay, take the Hernantian period. This was towards the end of the Ordovician period, roughly 445 million years ago. Fandier reconstructs a global mean surface temperature, or GMST, of about 21 degrees Celsius for that time.
21 degrees Celsius. Okay, for comparison, what's our current average?
Our current interglacial period, the Holocene, has a global mean of roughly 14 degrees C, so 21 degrees sounds pretty warm, right? 7 degrees warmer than today on average.
That definitely sounds warm.
Yet, and this is the kicker, the geological evidence, like glacial deposits and sea level changes from that time, strongly suggests there was extensive glaciation during the Hernantian. Massive ice sheets.
Wait a minute. So how can a warm Earth, globally averaging 21 degrees C, have massive ice sheets?
Yeah.
That genuinely surprises me. How does that work?
It seems contradictory, right?
Yeah.
But this highlights a really important point about latitudinal temperature gradients, how temperature differs between the equator and the poles, and also paleogeography, which is just where the continents happen to be located back then.
Okay.
The 21 degrees C global average during the Hernantian appears to have been largely driven by very, very warm tropics. So the equator was hot, but here's the key. Because of the arrangement of continents at the time, there was this huge continuous landmass, part of the supercontinent Gondwana, situated right over the South Pole at high southern latitude.
Big continent at the pole.
Exactly. And this unique continental configuration allowed for intense regional cooling and the buildup of massive ice sheets right there at the pole, even while the global average temperature was relatively high because the tropics were so warm.
So the heat wasn't evenly spread out.
Precisely. It was concentrated more towards the equator, allowing the polar regions, especially with that landmass there, to still get very cold and support large glaciers. It's a crucial nuance.
Fascinating. Does this apply to hothouse periods too?
Yes, we see a similar kind of nuance, but sort of in reverse, with hothouse climates. For example, during the Indian period, which is right at the beginning of the Triassic period after a major extinction, the Earth had the giant supercontinent Pangaea. This meant vast continuous landmasses stretching across much of the globe. Now, the Fandier global mean temperature for the Indian might have actually been a bit lower than some other hothouse periods later on. But because of that Pangaea configuration, with huge continental interiors far from the moderating influence of oceans, this led to more widespread regions experiencing truly extreme heat. The study mentions model results over 45 degrees Celsius, which is incredibly hot.
45 degrees Celsius, like Death Valley temperatures, but maybe more widespread.
Potentially, yes. Possibly limiting where complex life could even survive, creating lethal hot zones. In contrast, if you look at later hothouse periods, like the Turonian in the Cretaceous or the Paleocene-Eocene thermal maximum (PTM), the continents were more fragmented, more broken up. This allowed for more regional variation in temperature, more ocean circulation influence, even if the overall global average might have been higher than the Indian.
So a higher average doesn't necessarily mean worse everywhere.
Not necessarily. It highlights that a single number, the global mean temperature, doesn't tell the whole story about habitability for life or the prevalence of extreme conditions. The geography, the arrangement of land and sea matters immensely.
What an incredible journey through Earth's really deep past. This deep dive into the work of Emily J. Judd and her team. It just shows us that figuring out Earth's temperature history is such a monumental task.
It really is.
Combining these super sophisticated computer models with just meticulous, painstaking analysis of tiny chemical clues locked away for 500 million years.
It truly underscores the immense complexity of Earth's climate system, doesn't it? It's never just about a single global temperature number. It's this dynamic interplay of atmospheric chemistry, CO2 levels, ocean currents, ice sheets, solar input, and even the shifting continents themselves.
Yeah?
And how all these factors interact to create vastly different regional conditions across the planet. These nuances really help us understand how seemingly contradictory situations like a warm global average coexisting with extensive ice sheets can actually happen.
Or how a slightly lower global average, like in the Indian, could still lead to widespread extreme regional heat because of the geography.
Exactly. The context is everything.
And what's really powerful here, it seems, is that this framework, this fan day approach, isn't static. It could be continuously updated, right?
That's a great point. As new proxy data are discovered and published, as our fundamental understanding of how these ancient natural thermometers actually work improves, as we refine our models of plate tectonics and Earth systems, we can feed that new information back into this data assimilation framework and perpetually refine our understanding of Earth's deep climate history. It's designed to be a living, evolving picture of the past.
That's fantastic. So for you, our listener, perhaps this deep dive offers a compelling challenge, something to think about. How might our current planetary geography, the specific arrangement of continents and oceans we have today, influence how future warming and extreme temperatures manifest in different regions, even as the global average continues to change?
That's a crucial question.
What unexpected effects might regional geography play in our future climate, and how might that shape the human experience differently depending on where you are? That's all for this deep dive. Thank you so much for joining us.
Thank you.
We hope you're leaving with some new insights and definitely plenty to ponder about our planet's incredibly dynamic past and future.